right. So again, this is a relatively short lesson on radians, which is an alternative angle unit instead of degrees. So really, when you start looking, at any discussions about radians and trying to understand where all this stuff comes from, really it comes from thousands of years ago, more than likely. Geometry was considered a sacred mathematics, ancient, primarily because they knew that most of the stuff that involved the stars and the planets involved geometry. Because they had a sense that moon was circular. I'm sure at some point they reasoned that it was probably a sphere. They knew the planets' paths were circular. There was an awful lot of mathematicians back even before Pythagoras that spent a lot of time trying to decipher some of the mathematical laws that relate to geometry. And so really, this discussion really takes us back thousands of years when you start talking about what radians are and what's the history of it, and why do we use it. So imagine a circle, and they did an awful lot. There was literally thousands of years once they discovered that there was some constant of nature, some geometrical constant that at some point got called pi. I mean, who decided that? I don't know. Be interesting to Google it, see if that's known. But they were on to the fact that there was some number that was a special and unique number that involved circles specifically in geometry that we now know as pi, and they were on to that thousands of years ago. That's not my best, Joey. That's not my best circle, is it? Slacking. We'll try harder. Lock the elbow, rotate. That's better. Little better. Still not perfect, but better. So they had done, of course they were drawing circles in the sand, I'm sure, or drawing, etching circles into things. And they ultimately would try to measure circumference, right, which you guys know is the distance around, which was challenging because it's a curved path, right? Measuring a straight line is simple. They had, ropes and, strings and all sorts of stuff that came from the forest, thousands of years ago. That would be very easy to measure a linear distance. But how do you go about measuring a circle around? You can imagine that maybe they would put posts, a piece of wood. I can imagine them hammering in a piece of wood as posts into the ground, and then taking their string and wrapping their string from post to post. But they would pretty quickly realize that measuring now the side, summation of the sides clearly would not be a very good approximation to the circumference. So what would they have done next if this was their approach, which is to take some rope, and the straight lines represent the rope. The circle is what they've inscribed maybe in the sand or in the dirt or wherever. I don't know where they did that. And then the black dots are stakes, wooden stakes. Yeah. Add more stakes. You got it. That's exactly what you would do. They realized that if they had added more stakes, as Jaden suggests, that's not quite where it was supposed to be, but close enough. And now you wrap your rope. And now if they measured the physical lengths of all of those straight lines, they realized that would get a lot closer. That would be a lot closer approximation of the full distance around a circle. But not quite exactly. Underestimating or overestimating? Under. What would they have had to do to get their approximation even closer? Add more stakes. Yep, add more stakes. So there was certainly a lot going on again with them recognize that circumference, that the radius of a circle, diameter of a circle, that there was some mathematical connection between them. And so they surely did, experiments, maybe not scientific experiments, but mathematical experiments for sure, probably tons of them. And so I'm going to share one with you. One of those mathematical experiments that they would have done would have been after drawing a circle, you can draw out a radius from here to here. And then mark the halfway mark for the R and mark this halfway mark for the R and draw the same sort of curve now. That's actually very terrible. Not quite as close, not quite where it's supposed to be. More like here. And yeah, still not quite, but yeah, it kind of matters. Give me one more shot. I'm trying to make it like the half, right or at the halfway mark, so it makes sense. Yeah, that's probably better. So after they had made these marks and drawn these shapes that I'm drawing, they realized that let's just say they measured this, and what their units were, I have no idea. Another interesting thing that you could Google. What was the length unit? I know in the Bible, it's cubits. They used cubits to measure things. I mean, that goes back to 5,000 years. Whether Egyptians and things were using cubits, I don't know. They had their own measurements, units for length. Let's just make it a more, modernized example. Let's just say this was 10 inches from here to here. And let's just say this is also 10 inches from here to here, because they marked the halfway. This was the 1/2 R spot, where R, of course, is the full length, right? From here to here. So they marked the 1/2 R. Then what they would do is, well, measuring R shows us that R would have been actually 20 inches, right? 10 plus 10 gives us 20. Then they would have, what they're essentially doing is in this little shape, they're trying to relate three things. They're trying to relate the length of this curve here, which now has the word arc length, which you should become aware of. We're going to use that in physics. The length of an arc has a curve to it, and the length is a physical distance along the curve. This could be, I don't know, 2 inches, and then from here to here might be another 2 inches, and there's some physical length. Just because it's curved doesn't mean you can't measure it. It's more challenging to measure it, but it still has, a length, still a distance. If you walk around a rotary, you're still walking some distance, even if it's a circle, right? And so what they discovered that there was a connection between arc length. Arc length has the symbol S. This is the symbol in math and physics for arc length. And they discovered that essentially their question was, what is the relationship between S, which is this distance, and R, which is maybe the full distance? Is there some mathematical connection between the distance between the center of the circle and the edge of the circle and what this is right here? So when you do this, it's very interesting to find out that if this was, let's just say this was the 10-inch mark that we're seeing here in the middle. I'm just making this up. I don't really know how long it would be, but let's just say that they found out that this was, I don't know, 15 inches, this curve right here. What they found out is when they measured this other curve out here, they found out that, in my example, it would be 30 inches. So what they discovered was that when you look at the first chunk, which is right here, of this little pizza, that when you measure the R, which is for that particular part, is really a smaller circle in there that's now like this. So you're really comparing two circles. when you start with the first r, which is 10 inches, and you measure what s is, and I just made that number up, I don't know exactly what it would be, they then realized that if they doubled r from 10 inches to 20 inches, bringing it out here, that the arc length also doubles from 15 inches to 30 inches. So that was a discovery that arc, what was that? Well, you tell me, what was that? What were they discovering for the relationship between arc length and radius, if what I just said was true? If doubling the radius doubled the arc length? Yeah, it's one way of wording it, linear relationship, but what's another way? Yeah. Yeah, they're directly proportional. They discovered that S was essentially directly proportional to R. That if you doubled the radius of a circle for some, I'm going to say angle, there's an angle in here, because the angle is the same, right? Whatever this angle is, if this is a 45-degree angle, I don't know exactly what it looks like, maybe more like 60 degrees, but whatever the angle is for the small piece of pizza, that's the same angle for the larger piece of pizza, right? They share the same angle. So they realized that for some fixed angle, if R just gets dragged out twice as far, S goes twice as far. So what they started to wonder is, well, if S is proportional to R, when you recognize that something is proportional, it means that there has to be some sort of proportionality constant. If they're trying to create an equation that gives us what the length of S is, dependent upon how long R is, which is the physical length of, like this, they knew there must be something, again, it's called a proportionality constant. There's always something that's constant in all formulas. Like, think of just distance. Distance is proportional to time in terms of how far your car goes if you're going at a constant speed. If you drive for twice as long, you go twice as far, right? What's the constant? V. D equals VT. V is your constant speed. What about, what are some other examples? They are the same symbol. Yeah, they just use different ways. Yep. How about, F equals Kx? The spring force we know increases with how far you stretch it, but is there something that means Fs is the spring force is proportional to the length that you stretch it to, which we've learned that. What remains constant while you stretch it? The spring constant, right? There's always some number that stays fixed while one thing changes, it causes something else to change, but there's always something numerically, mathematically that stays fixed. It's called a proportionality constant. So they were interested in figuring out what this proportionality constant is. So what did they do next? The next thing to do is to imagine just saying, well, why don't we just swing this circle all the way around? I'm going to erase all this. Why don't we just grab this first one that's right here and just swing it all the way around? So they grabbed this one right here and just rotated it all the way around to here. So what were they doing? They said, let's just look at the whole entire circle. If we look at the whole entire circle, then the circumference of this whole circle becomes the arc length. Arc length can be a small section of the circle. It can be a larger section of the circle. It can actually be the whole entire circle if you're willing to rotate that thing all the way around. So that was their next step. Was rotating this thing all the way around. And what they started doing was they eventually did this method that we said earlier, which is using lots and lots of stakes and starting to focus on the whole circle as a whole. Because what I said on the right side, we're going to bring that back, this S equals KR in a second. What they started doing is saying, well, if we can measure their circumference, all the way around, they knew it was going to be a little bit underestimated because they never can put enough stakes to make it be exact. But they knew with enough stakes they could get C, the circumference, pretty close. And if they could measure this distance here, they rationalized with themselves that when we compare it with S equals KR, which is here, that R is the same. The arc length S is now just the circumference of the circle, which means that this value K right here, we should be able to solve for by just dividing the circumference by the radius. The radius was measurable. They could measure that. And the circumference, again, was measurable. They had a pretty close, way of doing that with all these stakes. So technically, again, if you just convert arc length into circumference, and R stays the same, then technically C divided by R should give you K. So they would set out and start doing it. Draw a bunch of circles, measure the circumference as much as you possibly can, and measure the radius. Divide the circumference by the radius. And they probably had tons of mathematicians all working on this problem, trying to figure this out. Guess what number they finally came up with that it was very close to? Close. Because we now, forward 5,000 years, we know what that formula is. C equals what, R? What is it? Close. 2 pi R. We know, we take it for granted. They must have worked so long to discover that. So when they did this circumference, which they were able to measure, divide by the radius, which they were able to measure, and kept doing it with more and more accuracy because they kept adding more and more stakes, they continued getting this number. And this number that kept coming out was 6.28. And what they found is that no matter what size circle they made, they could say, math guy number 1 or girl number 1, make a small circle, somebody else make a medium circle, somebody else make a big circle, and we're all going to do the same process. Measure the circumference, divide it by the radius. Let's get together afterwards and share our results. Everybody came back and said, I have this number, about 6.28. We now recognize what is 6.28. 2 pi, right? We now know 6.28 is actually 2 pi. So when you come back in here and say, all right, let's plug in that number, 2 pi, right here, we first of all recognize that that creates C equals 2 pi r, the circumference equals 2 pi r. Next, what we recognize is that this constant thing on the right side of the screen must be 2 pi. Well, how many things are there involved in a circle? I'm almost done with this. I think it's interesting. How many parts are there to a circle, or even to a section of a circle? Let's just go back to this picture that we had. There's one part, S. There's 2 parts, R. What's the only other third part? Huh? This one? But this is the same, actually. Those are both R. Which we call, what's the only other measurable part to a circle? The radius, this piece, the arc length, and the angle, right? An angle. So what they realized is, well, if the equation has 3 things in it, S equals KR, we know S was physically the arc length, R was the radius, then this K must be the angle, R. And now they came forward with this new concept of an angle. And then when they come back over to here, they said C equals 2 pi r. If you're going all the way around the circle, what is that angle going to be? Right? Because now, let me just write this last part. It's a little neater on this other side. If I were to rewrite this, what was already here? The same thing. The very last thing they realized, this was huge. This must have been enormous for them. They said, well, if S equals theta times R, because we started with S equals K times R, and we got this, and now we compare it for the whole, we return to the whole entire circle, which we now know was 2 pi R because we kept getting this number 6.28 from our experiments, then what must that angle for a full circle be? 2 pi. What do we call a full circle an angle? 360 degrees. But what is it going to be in radians? 2 pi. And that was the invention of this concept that there's an angle, there's a physical angle in here, and when you rotate it around the whole entire thing, that angle must be 2 pi. Because again, they kept getting 6.28 from these experiments where they were dividing the circumference divided by the radius. And they eventually said, that must be some sacred geometrical constant of nature. Eventually they realized that it was actually 2 times pi. Pi is really the geometrical constant. But it's proof that mathematically, when you do these experiments, the constant, again, for a full circle comes out as 2 pi. And that is the theta, that is the angle. So then you say, well, a full circle, which is 360 degrees, must have an angle of 2 pi. And those are called radians. With all of that said, you now have to become somebody who starts practicing these problems with radians. You'll have to know that 360 degrees is now 2 pi radians. Why do they call it radians? I can only guess that this involves the word radius, right? Radius is kind of radian, radius. It must come from that. They were radius of a circle. So 360 degrees, based on everything I just said, must have been equal to this mathematical number 6.28, which we now write as 2 pi. And therefore, 180 degrees, if we divide by 2 to both sides, 360 divided by 2 gives me 180 degrees. So 2 pi divided by 2 would give me pi. And this is just a chart that you can use, you can just keep dividing by 2. 180 degrees divided by 2 gives me 90 degrees. This must be pi over 2. Keep dividing by 2. 90 degrees divided by 2 is 45, which must be pi over 4. You could keep going. Be honest, after that, you have 22 degrees and 11 degrees, and nobody, at least in physics, we're not going to be doing stuff that's 11 degrees or 22 degrees. But I don't know, what would 60? We know that in physics, 30 degrees turns up a lot in our problems, 45 degrees turns up a lot in our problems, and 60 degrees turns up in our problems, and 90 degrees. So what would those be in radians? What would 30 degrees be? If we know 180 degrees is pi, what would 30 degrees be? "30 degrees is what fraction of 180 degrees? Yep, 1/6. Therefore, the radians must be 1/6 of pi, which we would write as pi divided by 6. And the shorthand for radians is just RAD. That's what we write for radians. How about, let's try 45 degrees. Well, I guess we had that one already right here, pi over 4. How about 60 degrees? "60 degrees fits into which of these numbers evenly? 360, 180, 90, and 45. What's the easiest one to choose? 60 fits into 180 how many times? 3. So that tells us 60 degrees is only 1/3 of 180, which means the corresponding radians must be 1/3 of pi, which we would usually write as pi over 3. Radians, RAD. How about the last one, which would be 90 degrees? Well, we had that on our table, pi over 2. Now, my point is, what's the only thing worth remembering? In my opinion, this one, because it's going to take you a little while to get used to this. It's a new unit. It's a new thing. I know it seems weird at first. Just know it has to do with geometry. There's this thing, again, called radians. It's a more fundamental unit for angle than this thing called degrees that we are used to. My point is, if you just remember 360 equals 2 pi, you can create any other one that you want just by following the process that I just did. So for me, would I, as a student, have memorized all of this stuff? No, I just knew that the top one was my key. And as soon as I had the key, I could open that door up and fill all those out later. Don't bother memorizing stuff that's unnecessary. Just remember one part. So I would recommend remembering that. That all said, once we are now going to use this in the assignment, in just a moment, I'm going to give you an assignment, give you the rest of the class to work on that assignment. Before I do, I will quickly go over those problems, if you can remind me of what they are. I think it was a spinning wheel. The angular acceleration, if I remember correctly, was 50 degrees per second squared. That means it's... Yeah, there was something that was originally sitting at this 45-degree mark, piece of tape, that was going to rotate around. And we were trying to see if we could predict where this little piece of tape mark was on this wheel some amount of seconds later. 10 seconds later, thank you. What was an omega, remember, represents the initial rotational speed. And it was 0. It was just a disk sitting at 0. The machine gets turned on and it starts spinning, but as it spins, it rotates faster and faster and faster and faster. So omega initial was 0. I would now write radians per, oh, I'm not going to do that, sorry. You guys were doing stuff in degrees, which is fine, but the rest of the problems we'll do today, you'll do radians. So we have degrees per second. Okay, and then what was the first question? The total angle. So I would like to point out that if you look at the position formula, sometimes they want you to tell, you're asked to determine where the final position of a car is. Car starts here at X initial, sometime later your car is here, and they want to know what is that position measured back from the 0 mark? What is X final? But sometimes they might just want to know what is the displacement delta X between X initial and X final. Maybe we don't care where its position is on the number line. We just want to know how far did it move in between X initial and X final. If you subtract X initial from both sides, what you end up with on the left side is X final minus X initial. Well, what is X final minus X initial? That is delta X. So that means this formula can also be written like this if all you're interested in is the displacement in that amount of seconds, the linear displacement. When they said find the total angle, we would call that the angular displacement. The total angular displacement means the total angle it rotated through in those 10 seconds. So technically we can write that as delta theta, because we take away X and put theta, equals omega initial t plus 1/2 alpha t squared. And then remember, since the disk starts at rest, 99% of the problems that show up on the AP exam involve a disk or something that's going to spin, but it starts out not moving. So not always, but most cases, you would cross this out. And that means the total angle will just be 1/2 alpha t squared. Just like, how far will a pencil fall in 3 seconds? 1/2 at squared. Really, it's the full linear displacement from where you dropped it t seconds later. So we would just plug those in. I'd have 1/2. Alpha was the number 50. And then I'd plug in 10 and square it. So I'd have 100 and times 50, I guess is 5,000. And a half of that, I guess, 2,500 degrees. So the total amount of angular degrees it rotated through is 2,500 degrees in how many seconds? In 10 seconds. The next question probably was how many rotations did it make, right? What's that? Full rotations. Yep. So when we say rotation, we mean one full spin around its axis. So we know that there's 360 degrees per one rotation, right? And we could technically now say, well, we have 2,500 degrees. So in that way, my degrees and degrees units would cancel, and I'd be left with, actually, that's the wrong way. I'd be left with 1 over rotation. So this is, yeah, sorry, I'm setting that up backwards. Should be the inverse of that. Because essentially you're just dividing it. You're dividing 300, seeing how many times does 360 fit into 2,500. If it was an answer of 720 degrees, and we said how many rotations is that, you'd say 720 divided by 360, 2 times, okay, it's 2 rotations. So really, that's what we're doing. 2,500 degrees divided by 360 degrees. And I don't know what that comes out as. Maybe somebody can tell me. 2,500 divided by 360 gives me 6.94. So how many full rotations? 6 full rotations. Is there a partial rotation after that in that last little bit of time? Yep, 0.94. It almost got itself all the way around one more rotation, but if someone said how many full rotations, you would say 6, right? How would we figure out how many degrees that 0.94 represents? Oh, I forgot about X initial. I was thinking it was 0. My apology. X, this part right here was, yep. Yeah, I'm so sorry. Thank you for saying that. I totally forgot that it started at 45 degrees, which means we would not. I mean, essentially, we would just subtract 45 degrees from our answer. But my apologies. So we would actually have wanted to stay with the way we had it. I have to back up to the beginning. Theta initial is actually 45 degrees. This term still gets canceled. And then alpha was still 50, and this was still 10. And so our final angle would have been what I had plus 45. What is it? 2,545 degrees. Yep. So sorry, and thank you for catching that. Now when I divide the total angle, actually, let's try to say. Well, no, actually, I take that back. I think about it. It depends on what the question is. Are they asking us where on the circle it is, or are they just asking us what is the total angle it rotated? So my answer, actually, now that I think about it, if it was just the total angle, would have been correct, right? Because it doesn't matter where you start on the circle. If we're just asking what is the total angle from that point around, then my answer would have been right, delta theta, right? Delta theta is just the total angle around. Again, this format becomes important right here if they were asking you, where on the circle is that piece of tape, 5 seconds later? Then this format would have been important because then you would have been able to do some stuff to work out exactly where on the circle in between 0 and 360 degrees it is. But if someone just says, what is the total angle? Actually, what I originally did would be right, delta theta. So I take it back again, sorry. So the answer would have been 2,500. And then my point was that if someone said, what percentage is that 0.94 representing? What is the angle associated with the 0.94? How do we figure out how much that is in degrees? I know it's 6 full rotations plus how many degrees? You say to somebody 0.94 rotations, they're like, okay, but that's not really that useful. How many degrees are we talking? 6 full rotations plus how many degrees? How do we do that with 0.94? Yeah, exactly. It's 94%. So I would do 0.94 times 360. I didn't ask that, but I'm just saying they might ask. That's how you would handle that. You'd say 0.94 times 360. It should be close to 360, right? And I get 338.4 degrees. So what's the total rotation? 6 full rotations plus another 338.4 degrees. If they had asked that, that's what you would do. And then what was the last question? What is the instantaneous rotation speed at 10 seconds? Is that what it was? Yeah. So remember, if it's 50 degrees, gaining a rotation speed of 50 degrees per second, then after 1 second, its rotation speed should have been 50 degrees per second. After 2 seconds, its rotation speed should have been 100 degrees per second. After 3 seconds, its rotation speed would have been 150 degrees per second. And every second, it's gaining rotational speed in the amount of an extra 50 degrees per second that it would rotate. So after 10 seconds, should be 10 times 50, right? So it'd be 500. And that does come from, that formula, V final equals V initial plus AT for linear motion. It's the same idea for constant acceleration. If it's 5 meters per second squared, then every second it gains 5 meters per second of speed. So for us, we would just put omega in there. This will get canceled out. And it's what what makes sense. You would multiply 50 times 10. And you would get, 500 degrees per second. So that would be that final rotational speed at the 10-second mark, which means if at that moment it stopped accelerating, because let's say it was a saw, saws don't keep accelerating forever, right? They eventually reach some top speed and then they just stay at that speed. That would be considered constant speed after that point. So if that was the top rotational speed, for each 1 second it continued rotating after that, it would rotate around 500 degrees. Not quite 2 full spins in 1 second, because that would be 720 degrees rather, but maybe 1.5, right? That means it should go through about 1.5 turns per second if that was a constant speed after it reached that top speed, just to give you that sense. All right, any questions about that? You guys will get the whole remainder of the class to work on a pretty good set, I think. It's a good, I think that'd be somewhat challenging, but it's doable, very doable. Oh, sorry. I'm going to post it right into Google Classroom, and you can have the rest of the time. I already posted for period. Actually, I might have posted it for both of you. Let me see. Yeah, he's got a whole bunch right here. Yep, of course. Yeah. I did not post it for you yet. I should have, but just post. You're welcome. Posted it for them. So let me, since I'm not on my computer, I guess download it to this computer from their spot. Yeah, I guess that makes sense. I wish there was. I haven't figured it out. Oh, it's useful because for me, I've never figured it out. Once I post it, it doesn't seem to give up that menu where I can now add other classes. It has to happen all at on the first post. Oh, I should ask her. Yeah, I don't know how to do that. That would be super cool, super useful. But this will just take a second. No, it's totally anything to keep time down with all of these things is useful. Oop, I don't know why it's saying this. Didn't mean to do that. Cut. All right. 8. Great. Assignment. Just remember that the whole assignment is everything is in radians. We won't talk about too much about degrees. I mean, we can reference it, but it's just know that everything's in radians. All right, you can refresh, and I'll tell you once you open it up what the problems are. We're going to skip down to the problem section. I very rarely assign those conceptual questions. Usually when I do assign them, it's from the problem section. So I'm going to ask you to try number 5, which is here on page 221. 5, 6, 7, and 9. 5, 6, 7, and 9. A couple of comments. Number 1, yep, it's all kinematic equations, all of it. It's a similar thing to like September, and you teach the kinematic equations and you give some word problems. It's exactly the same process, same formulas. One thing to watch out for and be aware of, you're going to see like in the first problem where they reference the rotational speed of a dentist drill, but this says REV/MIN. That means revolutions per minute. Usually it's written as RPM, but you can also write it as REV/ means per, MIN, minute. So if something is rotating at a RPM of 50 RPM, that means per 1 minute, per 60 seconds, it will rotate around its axis 50 full times, 50 full rotations. So there's a little extra work to be done with these problems because that's not omega. Omega the rotation speed has to be in radians per second. That's the unit it has to be in. It can't be in degree. I mean, again, we did those problems in degrees. It works, but you want to be metric system, and this textbook definitely wants you doing everything metric system, standard SI units. You have to be in radians per second for omega. So all I'm pointing out is you kind of have to think that through. I'll give you an example just to make it a little easier. Let's just say something rotates 60 revolutions per minute. You should really listen to what I'm saying. If something rotates 60 revolutions, goes around its axis 60 full times in 1 minute, we'd say 60 RPM. what would omega in radians per second be with just that information? Well, we know we can't be in minutes. We have to be per second for omega. If it's 60 RPM, then to figure out how many revolutions per 1 second, I would have to divide by 60, right? 60 divided by 60 tells me it's rotating 1 revolution per 1 second, which ultimately would be 60 revolutions per 60 seconds, which is 1 minute. Now, if I have it at the rotation rate at 1 revolution per second, how would I turn that into radians per second? Close. Not close. Totally correct. Multiply by 2 pi, because 6.28 is what you said. Yep, 2 pi is 6.28. I would recommend when you enter it into your calculator, just do the 2 and the pi, because you're thinking, well, for each revolution, that's a full rotation of 2 pi radians, like 360 degrees, but we're in radians. So if you knew again that it was rotating 1 revolution in 1 second, how many degrees is that in 1 second? If you want to think of it that way, 360 degrees per second. What would that be in radians per second? 2 pi radians per second, right? So ultimately, you're thinking that through by dividing by 60 to turn it into revolutions per second, and then multiplying by 2 pi to get it into radians per second. That has to happen. You can't stick that number like there, 2.51 times 10 to the in for omega. It's not the right unit. All your answers will be wrong. So be aware of that. It has to be in radians per second, and that's how you do that. That's how you can convert from revolutions per minute to revolutions per second, divide by 60, and then multiply by 2 pi to get it into radians per second. All right? That's the only thing that I would suggest. Oh, one other thing is like number 6. They don't, for some reason, put commas all the time. Like that's the number 3,600. I don't know why a lot of physics textbooks avoid the comma and they put a space in between where you would normally put a comma. So when you see that, 3 space 600, that's the number 3,600. What's that? Yeah, it might be. The other thing is I think that sometimes they write really big numbers, like 3, 600, 542, and some people want to be able to look very quickly and think, is that like hundreds million? Is that 100 billion? By putting the space, maybe it makes it easier for people to go 3, 6, 9 and count those. That's my guess, but I'm not 100% sure. Just know that, again, when you see the space, that's a comma. Those are the only things to look out for that I just mentioned. If you have questions, I certainly can help. You might not be ready for number 9. In fact, I know you're not, but I'd like you just to work on those first ones first. Near the last maybe 15 minutes, I'm going to just describe one more thing, which would open up number 9 to you. But for now, just try those out. 5, 6, 7. You're skipping 8. Skip 8. 5, 6, 7, 9. And this is homework, by the way, for you guys to try to finish for tomorrow. Most students in the other class came very close to finishing it, and some finished it in class. So you probably will. Most of you probably will. Tomorrow, when do we see each other? I guess that's 10:45. Well, I mean, Okay, I'm gonna give you guys just a little bit extra information if I could for number 9. So just find an image. So let's look at this image on the top right. Oh, sorry guys that you now have to look at all that. So we're just looking at this image on the top right to make sure you guys can hear me at home. Hello? Yeah, you can hear me. So that's essentially the image that I had shown you, right? In the beginning of me describing radians to you, there's this equation, which is worth knowing. It's worth writing that down. I think it's even on your AP equation sheet. S, which is the arc length, equals R times theta. Just know that theta has to be in radians, which again means the physical length of the curve, S. I don't know how long it is, but you could figure it out how long it is by just measuring it directly. Or if you know what the radius length is and what the angle in there is in radians, remember those are all numbers, like even pi is a number, 3.14. You can't directly measure S because it's too hard for you. You can just measure it indirectly by multiplying R times theta in radians, and it'll give you the length of whatever S actually is. Now let's imagine we're looking down at a rotary and a car, like you did this pivot lab where a car was driving around a rotary. So imagine this is the top view of that lab, and there's a car coming around, and we mark this as the first moment that we're checking, its position, and then we, frame, next frame, and then we stop this as our last frame. So the car has essentially moved from here to here. We might be interested in what is the speed? What is the normal speed in meters per second? Well, if you could track, how many meters are along this curve and time how long it took to go from here to here, distance divided by time, right? Assuming it's going at a constant speed, and I'm referencing this as a car like in that lab where it's going around at a constant speed. So if you knew what the distance was along S and you knew what the time was to go from one point to the next point, S divided by T should give you the speed. But how would we use this? Because you might say, I don't know how to measure S, it's too hard. Like in a lab, I'm going to give you guys a lab in Pivot Interactive that you're going to start working on tomorrow, which is going to involve this. Because R is easily measurable with a meter stick, and theta is easily measurable with a protractor. They're not going to give you a curved meter stick in there, right? So you can't directly measure S. It is in meters. Yep, S is in meters. Yep. So my point is, if the question again was, what is the speed of the car as it drove around this rotary, and the starting point was right here, and the ending point was right here, and you had a stopwatch to time it, but you just don't know what this distance is because all they've given you is a meter stick. Well, let's see what we can do here. If we divide the left side by T, S divided by T, what would the units be? S's distance, which Zoe just said is in meters, right? S is in meters. If I'm dividing the side by T, which is in seconds, meters per second, what would that be? Speed. So we can really imagine, again, dividing both sides of this formula by T, because you can do anything you want to a formula as long as you do the same thing to both sides. What are we doing to both sides? Dividing both sides by T. S divided by T is meters over seconds. That's V in terms of speed. So now we could erase S over T and just put V there. On the right side, we'd have theta over T. What are the units for theta? Radians. What are the units for T? Seconds. We're dividing the side again by T. We're ignoring the R and just noting that if it's theta divided by T, that's radians over seconds. What would that be? Radians per second. What quantity is that we've recently been taught? Radians per second is omega. So that means by dividing both sides by T, I can transform this formula into an S over T, which is actually V, the actual speed of the car. And then the theta over T is omega. So now I have a new formula, V equals R omega. I highly encourage you to write it down because it's what you would need for number 9. Number 9 asks you about the speed of the tip of a helicopter blade as the helicopter rotates, as the blades of a helicopter rotate. They ask you for the actual speed. If they want rotational speed, they'll say, find the rotational speed. If they just say, what is the normal speed, like they just say speed without any rotation word, that means they want the actual speed in meters per second. for a blade that's rotating around. And if they're referencing the tip of the blade, you would have to know what R is. And they give that to you in the problem. And you would use this formula, V equals R omega. Do they just tell you what omega is? No, they're going to tell you the RPMs, just like the other problems. They'll say this helicopter rotates at a 4,600 RPMs. And the radius from the center of the helicopter out to the edge of the blade is given. What is the linear speed, the meter per second speed of the tip of the blade? You would need to use this V equals R omega. So it's a nice tool, V equals R omega, to convert from omega, which is in radians per second, over to V, which is our old, standard old meter per second speed that we've worked with all year. V equals R omega. Very useful. And that's what I'll end with. V equals R omega is be needed for you guys to do number 9. So again, try to finish up that assignment, which is those problems plus number 9. And then tomorrow, I'm probably just going to give you the solutions to look at maybe over the weekend. And I'd rather have you guys work on a lab. We're going to do a pivot interactive lab, which involves all of this rotational stuff. So we'll work on that with tomorrow 30 minutes, and then you'll have the weekend plus Monday to finish it. Thank you for reminding me that. Shoot. No, I would never give you both things to do. Yeah, I forgot. Yeah. So maybe we have to wait for the lab until Tuesday, till Monday. Yeah, someone reminded me. Yeah, you do have the test, and I have it ready to go, and I am posting it Saturday morning. We'll still work on the lab tomorrow during 30 minutes, and then I guess we'll just come back to it the next week. Yep. All right, you have a great day too. Bye, Emma. Have a great day, Carly and Caitlin. See you later. Have a good day. I just wanted to say real quick.